So I think it's a good number. So the theory, maybe you must have been done theory, but when we actually comes to this software, it's a bit different because it is not always it's go with hand in hand, because we don't actually understood. Okay, so that's what I want to say. And Professor Gopal, actually the foreign faculty, he suggested some simple model, like you take some domains like soil domains, and maybe I'd like to say, uh, can we take a model? It's a black one. Yeah. So let's take a domain, soil domain of 10 meter, and also the depth of the soil we can take 10 meter. Let's assume it, this is our natural ground, and let's do it 3D analysis. It's not a problem. Okay, let's considering diameter of 0.5 meter. So now let's model this, and you will get the idea. Maybe let's try until running of this model. So as you know, you have a different program, so it's already inbuilt. So that's why no need to worry much about. Uh, it is 3D. Everything it's a 3D. It's a 3D. It's a 3D solid structure. Property module, assembly module, step, interactions, load, meshing, and job module. And at the end, you can see the post-mortem results. Okay, the visualization, you can get all the outputs. So now let's talk about the part module. So when you open any module, you have first this window, you can see it's a create part. If you go to the next, it's a property module, create property. If you go to the step module, you will have a create step. Interaction, if you go, there is a create interaction. The first key, the first option you have, go for either 3D axisymmetric or 2D analysis. So what do you prefer? See, for example, this one you can do it as a 2D also, as even sometime you can do it maybe the simplest way, like axisymmetric, like in soil domain of, it's let's say 5 meter, and this is a 10 meter. So this will be like a axisymmetric element. This will be like a axisymmetric element. Just you revolve it, you just put your hand and take a analysis. Put lateral load onto it, then it has to be. Yeah. Yes. No, you can, maybe in that case you can define the boundary conditions, and you can maybe like here maybe it's a purely zero depth. Because you have the soil that is trying to flow around the file when you apply the lateral load. Okay. So you the best you can probably do is to take an axis of symmetry through the middle of the file. Yes. But even then, the other direction becomes a problem. That's why people think. Okay. Right, sir. So maybe what I am talking, it's a generalized way. It is you can use this approach for not only file problems. You can use for other dams, modeling of the dams, water permeability problems. Like even if you look at the structure, it's a different problem. Okay, so all that we can use it in the, because mostly I don't want to keep my presentation, it's like a UT, which is, see, modeling of this files already available in UT. Okay, so I don't want to keep that same in my presentation. So because there you will not get much inputs, so that's why, that's the reason I'm making something elaborated way. So now this is a one approach. Also, you look at this planner, the whole model. So you take a quarter models, maybe like this, and this portion. You model it this quarter model, and you do it so that the computational cost may be reduced. Because if you say to run this model will take 1 hour, if you are modeling it only the quarter portion, you may get less than 15 minutes. You may get your results within 15 minutes. So you can do it like different way. Now, okay, let's try the 3D model and considering this. And
we should have idea about the coordinate system. Of course, most of you studied FEM, so the coordinates may be quite you might be familiar with the coordinate systems. So now you will go for this 3D, and if you look at it here, there is a deformable, discrete rigid, analytical rigid, Eulerian model. See, we have a three different actually specifically analysis like Eulerian, Lagrangian, and arbitrary Eulerian Lagrangian model. These three things actually we considered. But if you see here, it's specifically mentioned about Eulerian model. If you want to do the Lagrangian analysis, that you can define it in the step module as well as during meshing. During meshing, there is a option standard. That standard that shows it is a Lagrangian. Okay, and further this arbitrary Eulerian Lagrangian model, that is a ALA, that you can define in the step module. That is the third module. If you look at here, here you can see third module. The step module you will have specifically Eulerian Lagrangian. Now let's talk about this deformable. Of course, the soil is a deformable. Okay, but the pile you can treat it as a rigid. So for that you choose any one, either discrete rigid or analytical rigid. So what will do this discrete rigid or analytical rigid? The analytical rigid, it is a purely rigid. No need to define any meshing. Nothing is required. No need to define the material properties. It work like a stone. Okay. So if you look at a discrete rigid, you have to define the mesh size. You have to do it, but it will work as like as rigid. Okay, so now let's talk about the deformable, and further you can see the base features like a shapes, whether it is a solid element, shell element, and a wire element, point element. It depends on the degree of freedom, how many degree of freedom you have. So what type of element, whether it is a bending element or it's something wire element, so there is no bending, it's like a beam element, truss element, right? So all this you can select any one. Now come to these options. As I told you, the revolution, what revolution, if you look at this problem, we can make it as a revolution. When you're modeling a spherical pipe, or you can say cylindrical pipes, you can model it as a revolution. Okay, you model it one thin line, just revolve it, you will get a pipe. So it's a modeling approach. Okay, and if you look at the extrusion is nothing but you just make a plate and just extrude it whatever height you want. Okay, there is option for extrusion. And then the sweep model, this also similarly, but it's a different functions. Now let's talk about the extrusion and this approximate size. It basically, there is a no unit system in Ambedkar. You can choose meter or millimeter, but you have to use standard. If you are following meter, you throughout the analysis you have to follow the meter. If you are following millimeter, throughout the analysis follow the millimeter. Okay, and my best experience, I may suggest you follow Newton per meter square, that is the best. And the mass density should be always kilogram per meter cube, so that the unit conversion and especially mass density that you have to keep in mind, and that should be kilogram per meter cube. So now this approximate size, let's say default to 200 I can take, or maybe 20 also. Now because we are preferring it's a 10 meter by 10 meter, or I can say 10 by 10 also, it's not a problem. This won't affect. You just get a grid with the size of 20 by 20. Okay, now let's continue this. This is the grid, 20 meter by 20 meter or 20 millimeter by 20 millimeter, whatever you assume it. Okay, now here you have option. You see, this is the point. To create any isolated points, you can use this, and this one for lines. See, you can make a rectangle by connecting 4 lines. Okay, or you can make a square by connecting 4 lines. So that's what is this key will help you, whereas this one will help you to draw the circular, either the circular raft or a circular soil layers. Okay, and this one for rectangle, as I told you, either through the line you make it, or just take it, drag it, so you will get a rectangle. Thereafter you can adjust the dimension as per your wish, so it's not a problem. And then elliptical shapes, or sometimes it's complex geometry, like a spherical or something, especially automobile sectors, they uses complex geometry. So for that you can do it all this with a trim, cutting, wetting, all this. Okay, now let's talk about this one, or let's talk about this one so that you will understand the coordinate systems. Now you start with maybe this will be like a 0, or you can take this will be like a origin. So this will be, you can say 0 comma 0. So just put, when you actually click this, you have options, you read this. See, for throughout this analysis you have to read the command, what you have to do next, that will give you. So pick a start point for the line or enter xy data. So now I am entering xy data as 0 comma 0. We got it right, 0 comma 0. Now let's come to this coordinate. Suppose this is, let's say x is a 10, y is 0. Okay, so now I am keeping it's a 10 comma 0. Okay, got it, this one. Now what about this coordinate? If I say this is a 0 and this is a x, and this would be, let's say in a big case, this is a z and this is a y. So, yeah, this is y. Okay, so what is the coordinate at this point? This would be, it is a 10 comma minus 10, 10 comma minus 10. So I'll type it's a 10 comma minus 10. Okay, it's come down, and then you can come to this line. It's going to be 0 comma minus 10. Then you can directly connect it here, or you put 0 comma 0, so you will get things. Now I have this plan. Okay, just click done, just click done. Sketch the section for the solid extrusion. I'm going to extrude this plane to 10 meter. Okay, so click this, will ask you depth. So this is the depth, so how much depth you have to go. So just click, it's 10. Okay, got it, that's it. So now there is a pile. See, basically we have, suppose when we are model the concrete, we don't model it like a reinforcement and a concrete. It's like, we have option to embed the reinforcement within the concrete. Okay, because it is a tightly connected, whereas in the soil it's not like that. We cannot just embed into this element, so we have to do cutting. So for the pile, it's like a borehole, right? We have to make a borehole. So how to do this borehole? In this you can see there is a shapes cut. Okay, and you can say extrude, because you have to cut it, maybe from here, you have to cut it from here. It will go maybe, let's say the 5 meter. What is the depth of the pile is 5 meter. Now let's go extrude. You read here, select a plane for the extruded cut. Okay, so here I am selecting it. Now select an edge or axis that will appear. Okay, so I'll select, I think, vertical on the right. It would be okay, I think. Yeah, you can see. Now you put it here, wherever you want to bore hole, you just put the diameter, so you will have bore hole now. Okay, so now let's take amps as a circle, and 0 comma 0, it is 0.5, let's say minus 0.5 comma minus minus 0.5 comma plus 0.5. Can I do it? You see here, it's a x, so I'm picking this 2 point. Okay, just done, and we'll ask you the depth. So throughout or some depth. So make it blind. So the depth is 5 meter. So now you are getting borehole of 5 meter. Okay, now borehole is ready. Now you have to create the pile so that you can insert your pile later. So now let's go to this create part. Now you can rename this we have a name part 1, rename it is soil. Now create pile, same deformable solid extrusion, continue. You can take a circular pile 0, 0 and minus 0.5, 0.5. Sorry, it's a 0.25. We kept a minus 0.5, right? So that means 1 meter diameter borehole we kept. Okay, sorry, that should be 0.25. So that now let's make it this as 1 meter diameter pile. Okay, let's make it 1 meter diameter pile so that your borehole is now 1 meter diameter. Now the pile also will be 1 meter diameter. Yeah, now this is done. Just cross this, done. We'll ask you the height. So it's a 5 meter, 5 meter depth of the pile. So you got the pile. So 1 meter diameter and a 5 meter depth of the pile. Now these two things are ready. That's all. Now we can move to the property module. So the property module, we can define the property. Okay. So basically this property, it's a very important, as you know how what inputs you are giving. Okay, the same output you will get. It's a very important that you have to select. That's why the constitutive model, it's a simple constitutive model, is stress is directly proportional to strain, right? This is a simple constitutive model. Now whatever you want to add, you can add. So you couple it and your material model will be strengthened by adding whatever, the strain rate, stress rate, state of stress, triaxiality, temperature, right? So you can improve the models. So there are two different models generally we have, that is a phenomenological model as well as physical based models. So anyway, don't go much into this material model because the structural mechanics we uses a bit different models. If you look at a phenomenological model like a Johnson-Hook model, KHL model, Arrhenius type model, and similarly the physical based model, it is a Armstrong model, like a some more models, and specifically for metals and a soil and a concrete, ceramic, we have different models. Okay, you can use for a soil like a Morkulo model and a Dreger model. These are the familiar model. So you have to characterize those parameters very precisely. Okay, so now if you look at this DP model, Dreger model, uh, yes, there is a constitutive model. It's a inbuilt already for porous material. It is available. Now let's go to the abacus. You can see. You go to this. Here you have to create the material. So now let's say the density of the soil, whatever soil. Okay, what is the density? It's approximately 1850 kilogram per meter cube. And now you can see here under mechanical you can find different materials, different material parameters. Okay, you go to the plasticity. Can you see here porous metal plasticity, creep model, swelling, viscous, more Coulomb plasticity model, Dreger model, right? So you can define, you can select whatever you like. But those material parameters is very important. You have to calibrate, you have to characterize. Otherwise, for example, I'll tell you, the concrete, we works extensively in India, the concrete damaged plasticity model. I couldn't find it last 15 years anyone characterizing the concrete. They just put a grade of concrete and gets a compressive strain, compressive stress versus strain behavior, and tensile strain versus behavior. That's it, and nobody did. Similarly, the soil also, I couldn't find it. They actually characterize even the Moore Coulomb model parameters. So because they just picks from the literature, and see, we need a very simple test, but of course some of the tests need advanced equipments. Okay, so you can select anyone. So now let's talk about the soil's elastic constant. The Young's modulus roughly 25 MPa. Young's modulus 25, it should be Newton meter square. Okay, 25 into 10 power 6, so we can make it 60. The Poisson's ratio 0.25 for the soil, 0.25 for the soil. Okay, you can keep, but this all you have to put to actual data. It's not like a randomly. Okay, so that you have to keep in mind. Now the elastic constants. Okay, now go to this mechanical plasticity parameters. You can choose any one, either Drager-Berger model or Moore Coulomb plasticity. For example, uh, we actually used both the model for the masonry walls because it's a clay brick walls. I'll show you videos. It just takes maybe couple of minutes. You see here. This is actually DP model, Drager-Berger model. This one is Moore Coulomb model. So you can understand how the difference in the failure pattern. It's a made by clay brick wall panels. Okay, you can say this is the walls we use as. Okay, maybe I'll stop at this stage. I'll stop at this stage. Now let's see the experimental video. Oh, sorry. Can you see here the failure of this wall? You can see, right, the failure pattern almost we are getting similar, but the impact force, it's a different. Maybe that video, the same video I can show you just so the how you see here in the DP model we are getting the impact force of almost 20 kilonewton, whereas the Moore Coulomb model we are getting about 40 kilonewton. So the huge difference, whereas the actual results we are getting this 20 kilonewton from the experiments. So this, why this slide I am showing here, mainly it will help you how these material parameters are important. Okay, though the both the model helps you predict the behavior of soils, but the nature is pretty different. Okay, so you can select any of the mechanical properties, and now I may not go because that you will take care yourself. Now let's talk about, this is a soil. Now let's create for concrete. General, the density is approximately 2500 kilogram per meter cube. The elastic properties you can take near about 25,000 near about. Okay, and this Poisson's ratio approximately 0.25. It's okay. So here for concrete you can use concrete damaged plasticity model, or as per wish. If you are using it as a rigid element, it doesn't matter. Okay, no need to define. Now the properties are created. Now you have to give the section. So now you go here, go to the create section, and here let's say soil, it's a homogeneous. See here we have options, whether if you are modeling like a water, then Euler-in model is more suitable. Okay, otherwise the soil we treat it as a homogeneous. Am I right? The soil will be treated as a homogeneous. If suppose you have a different layers, then what you have to do, you create either partition or do it separate models. Like suppose this, let's say first 2 meter it is a clay, you create a one model for 2 meter depth, okay, one element, and then you create another 2 meter, let's say sandy soil, and again another 2 meter, let's say rock. These tools partition, right? So what it is coming, you can see this is basically 3D element. So choose the cell. So define cutting plane use datum plane, create partition through datum plane. So click this, create partition through using datum plane. So now I have selected it. So what it command is, select a datum plane, select a datum plane. You see here this line you have to click, color changes, right? Create partition, that's it. So now the top layer is clay and bottom is whatever other different soil that you can define. Now this is one of the approach. Now the second approach, what I want to say, you try to model it separately, 5 meter depth soil separately and remaining bottom layer separately, like a clay and sandy soil. Then you assemble it all together and define the interaction properties. That interaction properties may be the general contact works very well, because if you go to the site, these layers are different. Okay, I don't think all three layers work homogeneously. It won't work homogeneous. It's not at all a homogeneous. So you have to define the interactions. See, if you put a soil over the rock, of course it behaves different. You know very well, because I have not studied it. So you know you know very well it behaves different. So when we do this actually, this is not actually correct approach. Okay, but anyway, we have a short of time, we are using this approach. Otherwise you have to do the detailed modeling, that will give you more precise and accurate results. Okay, now this is done. So now you go to this assign property, create, let's say select a regions to be assigned. So now top layer I have selected it, create soil. So here you have to define like a soil 1, soil 2, or sandy soil, clay soil, whatever you like. Okay, now it's done. Now the bottom layer you do it same, soil. Okay, so both the layers are now it is modeled. Now you can come to the assembly model. Yeah, this is a bit, you should have common sense. The assembly model, it is a purely common sense, where to place what. It's a very simple things. Okay, so create instances, click this. You have a two elements, one is a pile, another one is soil. So now let's keep the pile first. Pile, it came, yes. Now soil, you see your soil is here. Okay, just click OK. Now I am bringing pile, done. Now you see your pile is somewhere, okay, somewhere it is not exactly here. So you can translate the pile, also you can rotate the pile whatever direction you want. You want a anchor cable, you make it straight, but here while assembling it you can rotate it, and whatever angle you want you can use it. That's why you see here there is option translate. So you can translate the instances or the element from one place to another place. Okay, so now this one, let's rotate first, because the pile should be vertical. So now rotate first. So for that there is option, it is a rotate. Click rotate. Now what is the message? Select the instances to rotate. Okay, so I am selecting it, done. Now select an axis or start point of the rotation. How to rotate? Okay. So the start point, can we keep it here? This is the, oh sorry, is it correct? Just a minute. Hmm. So the start point is this. Now they are asking end point, how to rotate. Okay, how to rotate. Otherwise, for rotations, you can use axis. Okay, instead of start point, end point. See, you should be very clear what is your coordinates. If you would have been written the coordinates precisely, you can define it. Otherwise, you go with this axis. Okay, we'll get idea. Now let's say the axis is done 90 degree. That's not happening. Just a minute. Which had rotated this direction. Okay. We need a, the file is this direction, then we have to, just a minute, huh? The rotate, the file is this direction, right? We want this direction, so then x direction press karo. So 90 degree, yes, it came. The rotation is changed. Now I will translate. So it's a done. Okay, now done. Now you go to translate, click this, done. Now it is asking starting point, from which point to which point you have to start. So the starting point is center of this file. The end point is it this one? Yes. Now the file is inserted. Now the file is inserted. Now the assembly operation is complete. Now let's go to the step module. The step module, as usual, I told you, you first create steps. See, there are 3 different steps which you have to create. The first one, it is a general contact that you have to define, between the soil and the concrete surface. The second step you have to create for the gravitational force. The gravitational force which we going to, because it's a force, it's a gravitational force, right? So then the third step we have to create for the external force. As a professor was suggesting, you apply some live load. It's maybe the weight of the superstructure or the load reaction force comes from the superstructure. I think you have solved one problems with a 25 ton the load which is acting over the pile, right? So that way. So we will create 3 steps. So now let's create step 1. We can say it is for external load. Okay, the external load you can keep static general. See, here you can find different analysis. Okay, the external load, yes.
For these analyses,
Yes.
normally what we do is to create the geostatic stresses first.
Yes, sir. You can.
Otherwise, the fire will fail because the soil has
So
to
during,
strength.
yeah, but I don't think it impacts. You can, the order can be anything. Yeah, UT generally prefers that.
Normally, in all of
Geostatic.
mechanics, we use geostatic stress first.
Yes, sir. Geostatic first. Okay, let's keep that, but it won't impact. Yeah, it won't impact. Geostatic for the gravitational force of the soil as well as pile, that has to be given. Yes, sir. So this is the time increments, delta t, how the increment actually takes place. You can keep either automatic or fixed, and sometimes this you have to study carefully, because how much time your earthquake motions or the lateral load actually takes place, accordingly you have to define the time steps. Okay, and because it's a frequency related, so what frequency actually your simulation you want, that all you will get. So now the external load is created, and now you can go to the geostatic for your gravitational force due to the gravitational force in the pile as well as the soil. So geostatic you can keep automatic, it's not a problem. And another one is the interaction, that is a general contact between the soil and the pile, because these three things involved. So whenever you go for any new problems, you have to see carefully what all involves. Of course the gravitational force involves, of course the external force involves. Sometimes if there is a no soil, other things involves, then no need to go for geostatic in that case. So the step 3 I can say it is soil structure. Geostatic, yes. Sorry, it should not be geostatic. Soil structure should be general static. Yes. So the three things we have connected, and the step 2 it should be renamed as geostatic. So that's all. Now there are three steps that we have to take care in the next module, that is interaction module. Now here we have also the field output request. Okay, see you can find what you want. Sometimes we don't want much of the outputs, so no need to select all. See, if you want a stresses, you see the Mises stresses, other the principal stress, and there are different component of the stresses. Which one you want, you can just check in, so that will come in the output. Okay, otherwise don't check in all, it's of no point taking that much. Yes please. Bending moment, okay, we have options. You can come down the forces and reactions. Can you see here the moments and shear forces and other things? You can define it here, you will get in the output. Okay, yeah, it's already default selected. You can see, can you see here, check in? Okay, reaction force, the contacts, energies, failure mechanisms, whatever you like, you can select it. Okay, now let's close it. So you can see these keywords, actually this is the keywords. Okay, this keywords actually whatever you are selecting, the keyword corresponding to that it will be updated. So that keywords actually will help you to guess what is that. Yeah. So now next move to the interactions. So how to do interactions? So you have to define mainly the interaction between soil and pile. That is first thing. Second thing, if you have a layered soil, then layer to layer you have to define the interactions. So this interactions basically it's like one is a master surface, another one is a slave surface. Okay, see of course no element will go into another element. The soil will not enter concrete, the concrete will not enter soil. Okay, so the general surface to surface contact, it is more than sufficient. Otherwise you have to choose some other contacts. And for layer soil you can keep general contact. Suppose you look at here, create, you can see there are different contacts, like a general contact, surface to surface, self contact, and some more which actually I have not used. It's because it's a very big software, it's not like small bottle of water.
Does it do gap opening between the files and the stuff?
uh, Gap open,
Gap element.
gap element. Sir, in that case what I may suggest you,
Doesn't make one mask.
yeah, no, another way you can do it, um, the pile diameter you keep it, maybe it's a 499 millimeter.
No. It should not do that.
Ah,
Basically, when the file is oscillating,
yes sir.
then in one part of the cycle it will lose contact with the top layers of the shallow layers of the soil, right? So then a gap opens, and then in
Yes.
the another cycle it goes.
During no,
Yes.
it is which one? Which one? Large. But explicit, you can go for explicit analysis. It's a, but sometimes some of the models may not support explicit analysis. Suppose if you are going for a concrete pile, then you better take it as a rigid and don't define the steel reinforcement other things in the concrete, because the static general I think may not support for Johnson Hook model. So like that, some of the constraints always there, so that you have to look into it. So now let's talk about the surface to surface contact. Uh, Soil structure. Here you can see there are three things we have selected, right? So the external load, geostatic, and the soil structure. So these three things you can take. Soil structure first. Continue. Now it is asking you to select the main surface. Okay, that is a master surface. So let's treat this pile surface as a master surface. So you just go to the tools and display, create, and part module. You just remove the soil, you have pile, right? Now select the main surface. Yes, that's all. So all the surface which is going to be connected with the soil that we have selected. So done. And it should be always surface to surface, because for getting accurate results or better results you select surface to surface regions, not node to surface. So node to surface may not give you accurate. Of course, during my PhD, I used the node to node region to surface region also for the impact problems, but it gives a different results. So it's better to use surface to surface. So now the second surface should be your soil. So now just go to the tools and just remove this pile and bring the soil. See, if you are removing, adding, expect nothing going to happen. Okay, nothing going to happen. Your model will not be disturbed at any case. Now I'll select the surface, shift, and that's all. Now this is the complete borehole which I have selected. Okay, done. Now you have to define interactions I have to define. Before that, the contact I have to define and come, because that contact actually gives you the behavior of normal and tangential one. Okay, so now anyway, let's keep this. I'm keeping as it is. Okay, it's not accepting, so I have to create that first. So now I'll go there. This one you see here, read this interaction property manager. Here you have to go first, go to this and create, and yeah, the contact, mechanical behavior, tangential behavior. You have to keep, of course there is a friction right between the soil and other things, so the penalty based contact algorithm that you have to use it. So the friction coefficients, maybe you can keep it 0.2, 0.3, but this friction actually impact your results. So you have to take care, you cannot randomly put something. So this, oh sorry, another one we have to define, normal behavior, right? The normal behavior that we have to define, it's a hard contact, you can keep as it is default. Now the interaction property is defined. Now you go to manager, interaction manager, create the same steps what I have done, you just repeat. So now I'll go to this tools, display, create, remove, soil, add, select the main surface, then surface based one. Now go to the tools, display, create, file you can remove, add soil, sorry, is it selected? Oh yes, now it is done. It is selected now, the interaction property. Okay, that's all. Is it complete? Created, move left, it is activated now. This is the one thing. Now the second thing, we have to define like a gravitational force. Okay, uh, I think the interaction is only this much. That's fine, sufficient. No need to do anything further. Now let's go to the load module. There we'll use it geostatic steps because that will be the gravity loads. Is it boundary conditions? Okay, create gravity load. This should be geostatic. Geostatic, then the gravity load. Now continue. It's asking which direction we have to see. Just check. It's a y direction. Am I right? It's a y direction. So y directions. It's a 9.81. It should be minus. Yeah, it's because reverse. Minus 9.81. Okay. Now we lost. No, we have to select this. We are not selected it. I think this should be. I'll delete this. Create geostatic. Continue. Select this model. Can you see? We have to select it. Done. It's minus 9.81. Okay, here there is option for amplitude. Okay, sometimes if you have the load versus time, okay, those things you can feed it by using this. You see the tabular form, you can just fill it. Whatever data, xy data up to 1 lakhs, sorry, it's maybe 10 lakhs. The Excel sheet allowed up to 10 lakhs. So up to 10 lakhs data, so you can feed it. It's not a problem. Sorry, it's cancel this. Yeah. Can you see here now? This is actually gravitational load which we have defined already. Now let's take a pile. Yes. Now let's define the load into the pile also. Geostatic. Okay, continue. Select the model. This also 9.81. Yes. So the gravitational load is defined. Now let's talk about the mechanical load which is acting over the pile, maybe due to the superstructure. So the create, it's a pressure, but this should be external load. The step should be external load. Step should be external load. Continue. This is the surface which is acting. See, you can model the pile cap also. You put a pile cap over this and define the interactions with a sufficient coefficient of frictions, and then you put a load, or still you want to model it a structure also, like a maybe 5-story, 10-story, the small panels that you can model it, and you can apply the load as external load. So now this is done. So we'll ask you the magnitude. Now here I'll put 250 kilonewton, which is I think it's a plus. It should be plus. Here I think it's a plus. So also here you can, if you have any load versus time data, you can feed it here. Yes, it should be plus because our force is acting downward. Here you can see the hex or hex dominated, tetrahedral or wedge mesh. Three different options. The hexagonal mesh always it's a preferable that you can choose. It's a done. Now you can go to the element type. Here you can see the standard or explicit analysis. So you can select whatever you like. Okay, and then here you can find there is distortion control, hour class control. See, this is a very important things. Hour class control is a very important things. When you have, uh, especially when you have, the mesh size, the internal angle is less than 60. Also, if the internal angle is more than 135, it creates problem. This is the one thing. So you have to maintain that internal angle of any two lines. Okay, it should be below. It should not be below 60 degree. Also, it should not be more than 135 degree. Okay, fine. This is the one thing. Second thing, during running this analysis, there is a possibility for the distortion because of the excessive stress. Okay, so the element will be distorted. Once the element is distorted, your program will be terminated and it will not run further. So to avoid that, basically the meaning of this hour class, it is nothing but the excessive distortion. The excessive distortion is nothing but hour class. So this hour class effect has to be taken care by incorporating any one. Either the default you can select, but a default it won't actually impact on your simulation. So you try to use enhanced hour class or relaxed stiffness hour class or viscous stiffness, any one you select and you define some value, because this all will improve your simulations better results. And this is one thing. Also sometimes, because this hour class control mainly due to this reduced integration. I think you must have been studied in FEM, the Gauss integration, right? Gauss integration, right? 1 point integration, 2 point integration, 3 point integration. So this, the minimum we need at least a 2 point integration. So mostly what we do, reduced integration in the simulation. So actually the reduced integration is quite computationally, it's not costly, computationally better, but this creates hour class problems, excessive distortions. Okay, to eliminate this you can use fully integration. But when you use fully integration, what will happen, there is a high chance for the shear locking, because the shear stress and the strain, it is a predominant. Okay, so there also it's a shear locking, and here it is hour class. So you have to take care both whenever you do simulations. So now this is a sufficient, this sufficient inputs, and then the element deletion options, of course. That dead element or the excessive stressed element, that is to be deleted automatically by default. The system will delete while running it. And also the distortion control by adjusting the parameter, because you have to calibrate, maybe few trials you have to do with the coarser mesh, and then you have to go into converged or refined meshing. That's why that is called a mesh convergence study. It's a very important numerical analysis. You do any use any software, okay, either Plaxis or Ansys, Abacus. The mesh convergence is a very important that you have to take care. And also you can adjust the results by varying these inputs like a distortion control, hour class control, element deletions, maximum degradation, all this. So that's fine. And you can see here various family like a 3D stress, acoustic, cohesive. So you can select accordingly. Now it's done. Now we go to the meshing, region wise or part wise you can do meshing. That's all. Okay, now let's go to the pile, and the same way you just seed this. Seed is nothing but edges. Okay, you have to create the nodes. The objective of this nodes is to actually define the definition for solving the unknowns. So this also maybe same size I can keep. That's all. Now the controls you can use maybe hexagonal. That's fine. Element type, it's okay. The same standard analysis, and then you can change it as per your requirement. Now go to the meshing by region wise or part wise. Yes, that's it. Okay, now you can go to the optimization. It is maybe once you familiar with this procedure or the trials, then you can do the optimization. It's not a problem. So now there is a job manager. You can create If you have input, yes, sir.
You need to give the boundary conditions.
Ah, yeah, yeah. Sorry, we missed it. Yeah, yeah, yes. It will come to you. You will come to know as a error. Yeah. Yes. It is a tetrahedral element. It is a. I don't think any different types.
Same to C3
No.
is spread at the time.
C3D8R is a hexagonal element. It's R represent reduced integration, three-dimensional element, cubic. So like a T8, I think, sir. It's basically it's a single order. It starts with a T. It's not C. C is a hexagonal element. Tools display plot, right? Plot all. So now create boundary conditions. So already the load manager we have defined everything. Sorry, we missed it. The boundary conditions, let's create. Okay, it is for the initial boundary conditions we can define. Symmetry, it's okay. Just select the surface. Oh, sorry. Okay, so now I'll not model. I'll not consider this. Yeah. Yes, yes. So that's why we will define two different conditions. So the side of the soil will keep different conditions. Bottom will keep different conditions. So that the side actually we will not allow to go down. Sorry, we will allow to go down, but we will not allow to lateral displacement. Okay, that is the assumption we adopt. And at the bottom, I think we will keep restrained fully. The soil will not go further or no settlement. The conditions we can adopt. Gosh, this mouse is creating issues. Okay, done. So I'll keep the direction x and z is restrained. Okay, x and z. Okay, this two is restrained. Am I right? Oh, what is this? I think no. Unmet. Sorry. Is it within this, right? 1 minute. I think this should be soil structure. No. Huh? Acha, displacement. Yes, yes, you're right, you're right. Got it. Thank you. Now I'll define it. Hmm. Yes, now I'll keep this to 0, 0. Done. Now it's okay. Now it is done. Now at the bottom, I'll keep as fixed. Create and displacement. Huh?
I'm going to select the
Yeah, select the surface and then do it. So that's all. Mcaster also is okay. All three I'll keep 0. That's it. And also there is a settlement in the pile, right? If sometime that's what I think last 4 days I have listened to your lecture, maybe especially the kinematics and inertial effect. See, that's a very important things plays in this. So the kinematics, it's nothing but a you know um, the deflection or the movement of the soil. what I understood. So moment of the soil and pile, whereas the inertial effect is due to the response of the soil and pile due to the superstructure. So that we have to define. So if I'm defining some displacement in the pile, that directly related to the what sir was talking about, the inertial effect and kinematics. Am I right, sir? It's a bit because soil structure interaction problems. Maybe I'm not that.
The inertia, you need to create a mass on the top of the pile.
Mass. That force we have defined already.
Not just, it cannot be just force is vertical,
Yes, sir.
right? Because in FE, you can do force without mass. When you shake the whole sample, the whole
Domain.
because it's going to come as horizontal
Motion.
you need mass on the top. You need to kind of create a point mass and make it like
Deflection, some settlement.
so you get the inertial effect as well.
No, we have already defined the mass.
No, we haven't. We
No.
only defined the force.
Acha. Okay.
That is and you define it in the vertical direction. That is the external force coming from
Due to the superstructure.
You need to add. The only way you get these earthquake-related problems to get the inertial force, you need to create a long mass on it.
Okay.
So in FE, you don't need to create. You can just have a point mass, right? But make the point mass very big.
Very big.
100 tons.
Yeah, this maybe you can when you do it, it will.
Already disputed it. What is your non static analysis?
Yeah, yes, sir. We'll do it. We'll do it.
Then you can do the next step.
Yeah, exactly. So maybe the displacement in the y direction, we'll keep it something 0.1 millimeter. Sorry.
Don't define it.
Okay.
Let the file be whatever it wants.
Okay.
It will does not need to. Okay, now you
So you can create the jobs. If you have already some input files, you can directly feed it and you can run. Otherwise you can run the model. The model name, let's say job one, and you try to keep this multiple processor. Okay, 2, 3, above 2, it's always recommended. So otherwise it takes more time. And then the memory and other things, that's fine. So general things. So now let's submit and see the error. Something already. Yeah, good. Without error, I think it's running. So no, there is some error. What is that? Unable to open the file. I think some monitor you can see, but I don't think there is error. See, there is no. I think there is no error in the file. It may be computer something, the core and other things not supporting. That's it. Maybe we'll try it maybe after. Oh. I'll restart the computer and then we'll try. Maybe after tea breaks, it will.
I think it's complaining about the stream, but that doesn't kill the.
Yeah, that doesn't. So sometimes this. No, nothing, sir. It's something.
It has job, but it's not able to open the job.
It's sometimes the driver issue. It happens due to the driver issue in the.
That's we are in your hands.
No. I'll restart the computer and it will maybe after tea break. We'll show you the results. Yeah. I just save this file. Maybe it's D drive. D drive. Let's keep. temporary folder. Oh, I'll restart and I'll check, sir. It's fine. Maybe the same file I'll give you on your PC. Huh? No, 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 no. No, no. Actually, see, run this file and I'll restart the computer. And maybe after tea break, we can discuss further. Dr. Prince Karandeep, he will also give some demonstration. Uh, So further, if you have any doubts, we can discuss in detail about more, modeling process and other things. Okay. Shall we proceed? Yes. Right, sir. Reinforcement, let's say main reinforcement, and you create one stirrups or rings, okay, and one concrete element. That's it. This one is sufficient, and you can stretch it. Maybe you can make it 100 number, 200, 300, whatever number. It doesn't matter. Okay. Now we have one pile and a soil. You go to this particular component, you can see now another pile is there. Just okay. Now you can translate this file wherever you want. There is no problem. You can translate and you can place it whatever locations. So like a actual field conditions you can generate in your model. Okay. So this is the one thing. Similarly, the soil boundaries, as I told you, layered soil, you create layer wise and use it. Uh, now the error in this, what we are getting, can you read this? Error in the job, it's a too many attempts made for this increment. So anyone idea why this error? Anyone have idea for this error? Okay, in my experience, I'll tell you, this error may be due to two reasons mainly. The time increments which you have defined in the step module, which may not actually, may not actually sufficiently to carry out the analysis. How this step time will be calculated? Do you know anyone? Step time. Step time. Okay, suppose your event, the penetration or perforation or the motion takes place, let's say 1 second. Let's say 1 second. Now this 1 second, you can see this data maybe in terms of 100 frames, or maybe how this pile actually is moving, and during the pile movement how the soil is deforming. All this you can address like a frame by frame, frame by frame. So let's say your delta t time step, it may be 1 upon 100, 1 upon 100. So the t, let's say start with 0, 0 plus 1 upon 100. So this is the time step. I think time marching scheme, have you studied time marching scheme? Okay, implicit, explicit. Okay, it's a it's a detailed subject. So the FEM, it's it will take you to really, it's good. So this is the one thing. So too many the error rate actually showing too many attempts made for this increment. This is the one thing. The second thing, sometimes if your material properties is wrong, if you entered material properties like a density, Young's modulus, or insufficient material properties, that cause this error. The another thing, sometime the loading patterns, that's what actually professor was saying. If the loading pattern it is not actually maybe simultaneously it's occurring, okay, when time t is equal to 0, both gravity load, both load in the pile and acting all together plus external load all together, maybe that is one reasons, but I don't think that might be the reasons. But let's try, actually he was suggesting let's try the ramp load. So the ramp load, it is nothing but, you can see it starts with a 0 increasing for every time step. So how to define this? You can go to this load module, take this, click this load manager, create, maybe the external load you can define as the pressure, continue, select the surface, done. Can you see the ramp? The ramp, this is nothing but the ramp loading, the varying from 0 to highest. So how to define this? Just to click this one. There is a tabular form, continue, and time versus amplitude. Now, okay, let's go to this GIAN course file. It is Jalandhar. It is Jalandhar. It is Jalandhar. Okay. So this is one of the data I can say. You see this data. This is the acceleration versus time. How it is generated. You may have a look these videos. The tunnel we made, it is filled partially. It's not completely. We kept a layer, over layer. It's near about 0.6, means near about 0.3 meter. Near about 0.3 meter that was filled over the tunnel. Then we have studied the response. So now the response is, assume it this one. So your acceleration versus time, two different locations. Okay, let's assume it two different locations. So directly you may copy this and paste it. This is also one way it will help you. Or otherwise, you just a time frame, let's say time when time t is equal to 0, you take amplitude, let's say 0, when time, let's say 0.1 second, your amplitude may be 100, right? When it is 0.2, maybe it's 200. When it is time 0.3, 300. So like that you can define the ramp loading, that's called amplitude, and done. Data not complete, so uniform. So it is okay, magnitude we have to put something, magnitude, it is the highest magnitude. Now let's run this file, and this is a quite common error. This you know, too many attempts made for this increment, it's a quite common error, so no need to worry about this. Now let's run and check. See the same error. Okay. Okay. Anyway, let professor comes. By the time we'll have this PPT. Okay. So if you look at the part module, you have to model the elements part wise. Then there is a property module, so you model it, the properties, then the section you have to define, then assign it, and then come to the assembly. You can assemble it, both the reinforcement as well as steel, concrete, whatever it may be. Then you can go for steps like a static or dynamic, whatever you select. Thereafter the interaction that you have to define. And further you can define the load. After that the meshing involves, it's what we discussed. Then you can run the file, that's it. So this is the basic steps basically involves while modeling this. Now let's, sir, we have tried the same problem. So this is the error we are getting, that too many attempts made for this increment.
So you try to apply the G load.
Yeah, yes sir, we tried this one. Can you please have a look to this one? This is the incremental load. So edit, this one we have defined it at this point.
But does it not run the jobs in C++? I'm talking about it.
Okay.
So you need to do that for load 1, load 2, everything, no? It is.
So this is actually
Geostatic stress.
oh,
Where it's you're trying to apply all the come down instantaneous.
Acha, you are okay. This amplitude which I have created, the ramp load, this one. Yeah. Okay, we have created.
And do the same for what is load 2?
Load 2, I think this is a pile.
Okay, then do the same for it, not instantaneous.
Okay.
Already up.
No, this is the external load.
Avoid instantaneous, just do it by that.
Sir, I think this 250 became a Newton. Now it should be kilonewton, right?
Yeah.
So then it should be another 30. Yeah, 30.
But don't apply it instantaneous.
Acha, this also to be okay.
Yeah.
Now all are amplitude. Sir, can you please have a look the amplitude which we have defined. This is the amplitude. The time we kept like a point.
That is in seconds, right?
Yeah, second. And this one, or can we keep it like a 0 to 0.3, 0 to 1? So that will become like a ramp, normalized.
I understand. Is whether you want to increase the time. Can you just edit it?
Oh, yes, sir, we can edit it.
So just make that 1 second.
Okay, 1 second.
Just make it slow as well. 100.
Okay, 100. You want to go further?
2 seconds, 200 seconds. Like that. The amplitude is this in newtons or what?
Sir, basically, suppose if you are defining this amplitude in terms of displacement, then it should be a meter. If it is acceleration, then meter per second square. Then if it is mass, then kilogram.
Yeah, but for this problem, what is the amplitude mean? Is it force amplitude or the displacement amplitude?
It is a force amplitude.
Force, right? Why is it in, are these newtons then? Everything is in newtons.
Yes, we'll make it, I think, kilonewtons.
Yeah. you need to be consistent. You said it yourself.
Yes, it should be consistent. Let's try. Let's try. Yes, sir. Oh, same error.
Open the output file.
Okay. Um, it means input file, right, sir?
Input.
No, output will not.
It won't create
It
anything
won't create,
until
sir. That's what I want to tell you. So when we run the file, this all the supporting files that generates, right, sir? So in the supporting file, of course, you have to note down there are 5 files are very important. Let's talk about ODB. It's output database. This is the first thing important output file. Second is INP .inp. It is an input file, and then this JNL journal file. It's a supporting file of CAE. CAE is this one. So CAE is this one. So these 5 files are very important, including status file. This one. So
why did you open that?
yeah,
See what is there.
status, you can see the, yes sir, it is coming like this. So further 0.0039 time increment, it's not able to process.
It's not converging.
Yes sir, it's not converging.
What is there? Go to your stepping, stepping thing you chose.
Yeah, exactly.
Stream automatic.
Before you come, I was discussing about the problem only starts from here, sir. So this one, suppose if you see here, whatever we kept initial and maximum time steps.
So run it as hooks rather than automatic.
Okay.
And just try one.
I think we'll keep all suffix and points.
On the point, another.
Fixed time increment is too large.
Go back. We'll try once more.
Yes, sir. Uh,
Increment size.
Sir, we'll go to check the status file. We'll,
Just leave the increment size 0.0001.
is it okay, sir? Is it only one or all cases?
You have to take all that.
So it's nothing. I think this geostatic, it's okay.
If that doesn't work, I don't know what to do. I'm not an expert in that.
No, no, sir. Sir, this error we face us many times. Oh, now this same error. It's not a problem, sir. Maybe I'll resolve it and I'll put it in the group later. Yeah.
Yeah, it's hard to resolve real thing.
Sir, there might be issue with the material property also. Huh?
Quite small times if you get, right?
Yes, sir.
What does data check do?
What, sir? Acha, data check. No, no, data check generally, sir, we before submitting the file, we can check the data, whether all the things are appropriate or not. That will get confirmation. Okay, yeah, sure, sir. So this will give you input file. Generate the input file. That's it. Yes, sir. So now you will get data check completed. So here you can see the data checking.
Running.
Check running. Yes, sir.
So clearly there's something wrong, isn't it? It's finishing that.
Yes, sir.
Basically, you have explained.
Sir.
Yeah.
Yes, sir.
The,
Let complete and then we'll. Yes, sir. Yes, sir. Yes, sir. Data checking is taking too much time. So we're talking about that.
what all the input file you created,
Hmm.
and see if all the data is consistent or not. It's not completing that.
Hmm.
So your input, the file and the soil interface, you created the master and slave surface, right?
Yes, sir.
Is the length of the file and the size of the hole correct?
Yes, yes, exactly. It's 1 meter diameter.
And 5 meter the file.
Yes, 5 meter.
And the hole is also 5 meters.
Yes, sir.
What?
Hmm.
Yeah, there's something wrong.
Hmm.
Even this, if this doesn't run, surely the another.
All right, sir. Then let's I'll keep the laptop side. So let get a complete thing, sir. Then yes. Hmm. Oh, you can.
लोड जो है उधर एक्टिव
Okay, we'll check after completing this. You want this? Okay. Oh, data check is. Yes, sir. No problem, sir. It's okay. We'll keep it here. Hard disk. Sorry.
Thank you, sir, for inviting me here, and thank you, sir, for here. And so I'm going to discuss the pile ring raft foundation here. So we are going to see how the model is developed, how the forces are applied. Okay. So first I will define the what the problem is, and according to that we will proceed further. Hey, chale. I क्या है यार इसमें?
विंडो की कौन सी
है?
विंडो की
ये है ई। डुप्लीकेट सेकेंड। हाँ,
इसकी आ रही है
ये किसका है? यही इसका ही।
सही है ये लगी है इसमें
हाँ हाँ, इसका एक साथ यूज कर।
एक ही पोर्ट है ना सर इसमें
हाँ, एक ही है। ये चलती है पोर्ट वैसे। दूसरी तरफ लगा के देखें, पर सर की चल रही थी।
लग ही रहा था उसी से
हाँ। So the problem is over. That is a ring foundation, and 4 piles are there. So this pile ring foundation is in the soft clay. Okay. So here, as already sir told you, that in order to save the computational time or the simulation time, we only do the quarter part simulation on the quarter part. So we are going to do the simulation only this part. Okay. So I am going to show you how the parts was made, then how the interaction was done, how the load was applied. Okay. So program is already there. Okay. So step by step I will show you. So this is the quarter portion of the ring. This is a pile. The diameter of pile is 300 mm. The length is 6 meters. In this ring, the diameter of total ring is 6 meters, and internal diameter. There are the two diameters. One is external, another one is the internal. The internal diameter is 2.4 meters. So this is a soil profile. So you can see that I have done this partition before before the assembling. So this is the pile hole. So this is a pile hole. Okay. So this is the location of the pile under the raft. So this is the center point. The pile is at this point. Okay. So we are simulation this part only. After the properties are there. First is the concrete property. Density is 2500 mm. Then elasticity is 34 GPa. Okay. The Poisson's ratio of this concrete is 0.2. So we have taken this value from some journal paper. Then of clay. Clay density is there. Density is 1800 kg per meter. Then elastic modulus is there, that is 5000 kilonewton per meter square. Then Poisson's ratio is 0.3. Then I used Mohr column. Then the angle of friction of the clay is 20. This is the drained clay. The value of C is 3. Huh? What about? It's a drained. The clay is already drained. So if it's undrained, then we can go for that part, but no need to do here. Then this assembly is there. You have seen already how to do the assembly. So uh, to get the finer mesh near the structure and the coarser away from the structure. Okay. If you have the finer mesh all over the soil domain and as well on the structure, then your computational time will be, it will may take my 2 days, 3 days, or maybe 1 day. Okay. Yes, yes. I will show you how we are doing. Okay. So the position of pile inside the borehole. Then this is a ring. Then I will remove the soil and show you the pile ring form. This is how we have made this thing. It is at the center of the raft. After this, there is a step point. So there is an initial step. Then to apply the gravity load, I choose the general static for the gravity load. Then to apply the final load, then I again choose the general static. So the incrementation, I have changed this incrementation. The initial increment of 1 second, the time is 1 second. The initial increment of the 1 second is 0.001. Minimum is 10 raised to power minus 10. Then maximum is 0.1. After step, the interaction part comes. This is the master, red in color, the bottom of the pile, and slave is the soil. This part is the slave part. Okay. Similarly, for the pile circumference will be the master, and the hole inside is the slave part. So now I will show you the interaction properties which I have taken for this. First interaction properties for the this raft foundation. This tangential behavior as well as the normal behavior. For that tangential behavior, the coefficient of friction is 0.3. You can go for 0.2, 0.1, 0.4, 0.5. Okay, as per your requirement, because you have to validate this model with some experimental part, and according to that, this coefficient may change. Okay, and somebody already has said that for the clay, you can use 0.3 as a coefficient of friction, like for soft clay. So normal part is hard contact and allow the separation after contact. As sir you said, if I apply the lateral load, so separation is allowed, sir. It is allowed by default. And for the pile, I used only the tangential behavior. Okay, because my soil is a soft soil, so friction pile is there, so only the tangential behavior will be there. So I am using only this tangential behavior. Okay. After this, the first step is to apply the geostatic stress. So how I applied the geostatic stress? Geostatic stress means at the initial step you have to apply the geostatic stress. As I already told, first geostatic stress should be applied. So we applied the first geostatic stress, then gravity, then the load. So magnitude of stress means 0 at the top, 0 at the bottom is minus 211,896. Okay, so we assume that literal coefficient is same, so I only taken the literal coefficient of 0.65, and 12 here is the height of the depth of the soil domain. After this, I applied the gravity load. Okay, the gravity load is minus 9.81. Then the boundary conditions. So I have already told you we are simulating the quarter portion. So how I applied, now I will explain. First boundary condition is y-axis symmetric. It means it is symmetric about the y, but translation in x and y direction is not allowed. Okay, suppose this is the part, this is x and this is y. So we are talking about the soil domain. We can say that it is symmetric about this y-axis, but the translation of in the soil in x and y direction is not allowed. Similarly, it is symmetric about the x-axis, but translation in x and y direction is not allowed. It means our boundary conditions are roller in the vertical direction and fixed on the bottom. So similarly, on the axis metric. Then, so I'm showing you one thing. This is the quarter part. Okay. Axis metric boundary condition and y symmetric boundary condition only can be applied on this face and this face. Okay. So to simulate the other part also, because we have taken the quarter portion, to simulate the other part, the axis metric only this face and this face can be taken. And what about these two other faces? This is the displacement option we have in the so in y u2 means the displacement is not allowed in the y direction, so it is simulating on other part. Similarly, this part, the translation is not allowed in the x direction. Similarly, this boundary condition, we use this boundary condition in caster, means u1, u2, u3, and r1, r2, r3 means the rotation and translation are not allowed in this part at the bottom. Okay, so you are getting it now. The axis metric means this part will we have assumed this quarter portion. So to simulate the other part that we have not taken in our simulation, we use axis metric on this face, y symmetric on this face. To model the opposite faces, we are using the displacement constraints. Okay, if it is an x direction, we are not allowing this translation motion in the x direction. If it is the y direction, we are not allowing the translation motion in the y direction. Then Plaxis gives the two options. One is prescribed displacement. You applied the displacement like 100 mm displacement. Your pile raft foundation or your pile will go up to 100 mm displacement, and whatever load is there, it will note automatically. The second is the load. You apply the load like 100 kilonewton per meter square. Okay, according that load, the displacement will come and it automatically will note, and you can draw the load settlement curves from there. So it cross means this part. See. So I allowed, now I am giving 1 meter as a prescribed displacement. It will go 1000 mm deep in the soil, so load will be accordingly. Okay. So the second is, with the gravity, you can also apply the pressure. Okay, this pressure is the 100 kilonewton per meter square. So you cannot use both. You have to go for either for the prescribed displacement or the pressure. If you go for the both, the Plaxis automatically go for the prescribed displacement. Sorry, Plaxis, I am saying this. Ambedkar will directly go for the prescribed displacement. After this, this meshing part is there. So see, near the structure, the mesh is finer, and away from the structure, the mesh is coarser. Okay, you can do this with the local seeding. So this is the point you select. Then, so see, either you can go for the by size. Size means the size of you can describe the size of this mesh, like 1 mm, 2 mm, 3 mm, or by the numbers. So the number of elements are the 15 and bias ratio is 5. Okay, bias ratio this uh, uh, controls this mass distribution. Okay, and this arrow is showing the mesh is finer towards the structure. If I change the direction of arrow towards opposite side, then the finer mesh will be on the opposite side, then the coarser mesh will be near the your structure. Then this is where do the global meshing. So I choose the global mesh size of 0.5. Now I will, so see, so this is showing the displacement U magnitude means all the directions of the soil as the raft shows the settlement, and the displacement of the soil under the raft. Okay, so you can see the impact and see the color. So we can clearly see as the raft goes down, there is an opening in the this ring, so soil will move out from that opening. So we have you can clearly see this from the final analysis. Okay, so now we can go for the load settlement curve. Or so in displacement, if you go for the prescribed displacement, there is one disadvantage, that is it treat the raft as a rigid. It will not show the differential settlement of the raft. So differential settlement is very important part. So if you apply the load on the pressure on the raft, then only it will show the differential settlement. Okay, the second point is you cannot find the bending moment of the raft, this pile, if you go for the solid. If you want to find the bending moment of the raft, then you have to choose the shell instead of the solid. Okay, so keep this thing in your mind, okay, while simulating this part. So you can see that this is a prescribed displacement results. So the magnitude, U magnitude is almost same. It means it is not showing the differential settlement in the raft. So this settlement in this part and this part is almost same. Very negligible difference is there. But if you go for the pressure, so you will see the major 1 mm, 2 mm difference is there. So we have observed that the inner part settles more than the outer part of this ring foundation under the uniform load. Okay, so if you see this is the important thing. Okay, all the values are nearly same. 0.001 mm is the only the difference. Then how to create a load settlement curve? This is XY data. Then ODB file field output. Then you will go for the unique node settlement. Then this reaction point 3. Reaction point 3 means in the third dimension reaction forces. So then you are going to collect. Then save. Oh no. We have selected 110 nodes. Then again you will go to XY data, then operate on XY data. Then we will sum all the reaction forces. So clear the expression. Now combine This x1 data is total of the reaction force. Then this, as I've already told you, the prescribed displacement. In prescribed displacement, the rigid foundation is there, so we can select any point. Okay, any point at any node. So displacement will be the same. So I'm selecting any point. Then plot the expression. So your curve will be like this. So force should be on the other side and displacement should be on the other side. So this is your curve. Okay. So you can also see this thing. Any doubt in this? Okay, thank you. Sir, it's reaction force is there now. It will be in the GIAN. So you have to divide it with the area of the. So at every node there is a different reaction force. Then you have to sum up all the reaction forces. So as U is the same at every point. So sir, it was prescribed displacement. The displacement was 100. Displacement was 1,000 mm. So according to that, yes sir. So we can go for 500, 200 mm, and I applied just to show the soil comes out from that in the. Oh, yeah.
No, what he wants is because you're punching the raft through the soft clay,
Yes sir.
and you have the space inside.
Inside, and not
The
suppressed.
clay will come out.
Come on.
You can see that.
Yes. So to show that, sir, to show that I increase the deflection, simply to show that. So
See what I want to say, instead of 500, 1000,
hmm
applying limiting deflection.
yes sir.
Limiting deflection for this PMM or 75
Yes, yes sir. We can go for it.
For that 75 what is their reactions? That would be like we can control it as.
You can go back and look at where is the force deflection in the plot.
Oh, okay.
Just now. That's where we are.
No, no, get the force.
1 into 10 to 6, that is 1000 kilonewtons.
1,000 kilonewton.
And the
You-
deflection is 0.25 meters.
Yes sir. No, 0.25 meter. I stopped the program at. Yes sir. That is the force. Yes sir. Yes sir.
Resistance of the brain formation.
Yes sir. Yes. Okay, thank you sir. Okay.
Stresses like the mysis stresses or stresses.
Mysis, it doesn't show in prescribed displacement. It shows only in if you apply the pressure. I will show you.
You will get it.
Yes, change it.
Yes.
You remove the brain body.
Okay, I will.
Remove the brain.
See, see, it doesn't show. No, it's showing in the pile.
That means your stress is very minimum.
Very minimum. Yes, yes, yes. Yes, yes.
You just need to adjust your axis range.
Okay.
So at the moment it's going from, it's in megapascals.
Mega 2.e. Minimum is
Megapascal.
yes.
Yeah, make it like 0 to 200 kPa or 300 kPa.
Then you can adjust by this
Yeah,
contour. Just a minute.
That's true.
You can adjust by just
those stresses are always bounded by
ये इधर से हो जाएगा, इधर से, हाँ ये वाला, हाँ
Everything is blue.
Just a minute.
पर मैंने देखा है उसमें आ जाता है ऐसे डिस्प्लेसमेंट वाले में।
Just a minute. There is an option for okay. Now let's see here.
नो ये तो
No, just cut section we can see. Next time.
हाँ यहाँ पे देखो, हाँ it's only showing in the pylon.
No. We can show the value also. Contour we can check.
वो तो we can check the values at the every point.
This limits. Specify the limits. Now say maximum, right?
Yes.
So it's maybe I'll keep it 6. I'll keep it 6, sir. So maybe
Plus 3.
okay.
It will be in kilopascals.
Yes.
So not in megapascals.
So how much I can keep, sir?
3.
3. Only 3.
No. Keep over 3.
Okay. Yeah. That's no.
It's still, it's not 90 gig, is it?
Yes sir.
Oh, I know what you have done. Have you still got the concrete point in there?
Yes, concrete
Yeah,
pipe
we
is
have to
there.
remove the concrete pipe.
हाँ
Yeah. Then you get.
वहीं से लगा हटा दो।
Fine.
Only soil.
Oh. Then no, still I think this is you see sir, this component they choose 3.4 means 0.3 MPa. 0.3 MPa.
रिड्यूस इट, इसको ये कर देते हैं इधर वाले
0.3 MPa.
इसको 1 देखो ना 1.1 है ये।
Why did you slice it like that? Why did you look at the whole room?
Okay.
To see the stresses inside.
No,
sir.
no problem. We can. 1 minute.
वो कहाँ गया? हाँ
Yes.
आ गया sir.
So now if you adjust this, maybe let's say 1000.
हाँ
Oh, it is quite high. Maybe.
yes
Minus stresses.
हाँ ये कहाँ से?
And also the principal stress is this. So sometimes this
Generally, in our analysis, we never do anywhere near tension. Yeah. Soil is not tension.
In this step you give all the details here, like length, it will be meter, mm, kilometer, whatever is force, you define the force, then time, second, minute, hour, day. Okay, so gravity is there, then water, if you change the unit here, then unit will change accordingly of unit weight of the water. Okay, so these are the coordinates. -15 means 15 meter by 15 meter is the soil domain. Okay, so after this there is a next step. So after this we have the this rectangular part, square part of this soil domain, that is 15 meter into 15 meter. Now we in 3 dimension we need the third dimension. Here you head is the water. If water is at 20 meter below the ground surface, you will write -20. If it is at the surface, it will remain 0. So you can change the depth of the water accordingly. Then add bottom top is 0, 0, bottom means the depth of the soil domain, like minus 30. After this, we assign the material. So there the number of constitutive models are there. Mohr column is there. Hardening of the soil is there. Soft soil is there. So we will go for the Mohr column. फिर there's another option: drained, undrained A, undrained B, undrained C, and they have mentioned the conditions of undrained A, undrained B, and undrained C. So suppose I select drained. So after you will put its general properties like unsaturated and saturated density. So I am writing the values. Sir, I am writing.
Yeah.
18 like it 0. So these are the soil. If you want to go for the further detail, you can put the kx, ky, kz values. Then second important is this interface, R inter. So if you put 0.7, 0.8, like in a Bakers we used 0.3. So 1 means the soil is very, the interface is very rough. Okay, 0.7 means 30% smoothness there or 70% roughness is there. So you have to find this value through direct shear test. Okay, using direct shear test, you can find the value interface between your concrete and the soil, and you can use that value here. Okay. Hmm? Hmm. Drained. These are drained values. C dash and phi dash are the drained. Drained cohesion, drained angle of friction. Then using this line, you can go for rectangular foundation, go for square foundation. Okay, and for the circular, you can use this. Then any diameter is there. So after creating this circular polycurve, then create a surface. After creating a surface, you will decide whether you will create a plate or this part you will treat as a plate, geogrid, okay, surface load, all. We will go for the plate. After creating the plate, we will assign the material properties. So D is the thickness of your raft, like we can say 0.2 meter. Then density of concrete is 25. Okay, 30. In Plexus, there are the two options. One, you can go for the pile. One, you can go for the volume pile. Another is the embedded beams. Okay, in my Plexus. I don't know, volume pile is part is not working, so I am going for the embedded beams. So this smaller part, this smaller red line will be the pile under this circular foundation. After this, the material will be assigned to the embedded beams. Diameter like 0.150. In order to get the skin friction in the embedded beam, you have to assign some values. Okay, otherwise it will not show any skin friction. Okay, so to get the skin friction, some values start maximum. There is some value you from where you have to start, or up to the maximum value. If you are not, if you are skipping this axial skin resistance part, keeping it at 0, and when you try to find after the analysis what is my skin friction, so you will not able to get. So some values you have to assign here. So I am assigning. So matching, you can go for medium mesh, coarse, very coarse, fine. I'm going for coarse. So this is how the mesh is generated. Our raft is very small. Its diameter is only of 6 meter, and domain is large. So that's the reason it is showing very small here. So behind this raft, this pink color body is your pile. After meshing, now how to apply the load? Like a baker's first gravitational load was first geostatic load was applied, then gravitational load was applied, then the main load was applied. So similar, the same we will use the same steps here. Like phase 1, I will go for embedded beams and plates. Then phase 2, we have not applied the load here. So on this surface, on the surface of the raft, we will click right, then create a prescribed displacement point load. So here you can go for the displacement you want, like minus 300. And in the, this is a very easy model in Plexus, because they are the very different things. You have to take the care thing of small to small part. But now in see Plexus, our model is ready for the simulation. So I'm sorry to say my Plexus doesn't run the simulation part. It will not run the simulation part. So only the construction part is here. So it's very simple software. Only 4 steps. Your model is ready, run, and you will get the results. Okay, thank you. Huh?
You write your own software in Ruby or are you using Flaxes? Flaxes can't do anything higher than triangular. I don't understand why. It's so tricky. Bentley people used to sell cars, bought Flaxes, and they're selling like cars to everybody. Now, PMS is not selling cars and it's not done.
Closing this session, we would like to take feedback. As already we have taken feedback also as per the format given by the GIAN. However, we like to take feedback from the participants in person if suppose if you're interested. So anybody interested for the feedback? Anybody is interested for feedback? Please come to the stage and you can give. Yes, please. Yeah, please introduce yourself and you can share your feedback.
Good evening, everybody. I am J. Yamini. I am research scholar from Indian Institute of Technology, Roorkee. And I thank GIAN for such a good opportunity. And we are able to know many things. And we have come to know what we don't know. I mean, as we grow old, we know what we don't know. That is the thing. And that's what I can say, that till now we have studied, like, generally we say that coin has two sides and you will see one side, but here we have many dimensions, multi dimensions. So until now we have seen some kind, and now, I mean, during these 5 days, we have seen the other dimensions of the research that has been conducted by Professor. And now we got some new objectives, new unknowns, and then I mean, definitely, I can feel that this will improve us, and like this is what research is all about. Like we have to know, and we have to find the solution for that, and I really feel very happy to be here, and we look forward to meet such professors and then share the knowledge and gain the knowledge. Thank you, sir. Thank you.
Yes, please. Please.
Hello, a very good evening to all of you. My name is Amankar. I am from research scholar in IIT Roorkee. I am also feeling the same. The NIT Jalandhar have given this opportunity to us to attend this course because it is very much related to my research topic also. I can tell you that that quiz, while seeing the quiz paper, if I get this on one first day, I will not be able to solve. I will be able to solve 10 to 20%. But now I have that type of knowledge so that I can think about that questions and attend all the problems. So, and thank you so much for this course. And also, I would like to thank Gopal sir because he patiently solved each and every query of us and provided every experiment. We generally learn theoretical knowledge from books, but he taught us about the from the experiment how can we learn the things and validate these theoretical knowledge. So, and thank you so much, sir. And also, I would like thank Professor Senthil sir and Agnihotri sir for this type of hospitality they provided us. Stay everything. It was very smooth for us. So, thank you so much, sir.
Hi, good afternoon, all. My name is Abel. I come from industry. I have completed my master's in earthquake engineering from IIT Roorkee. After that, I have been working as a structural engineer for 3 years. So, we design river bridges mostly, and we come across liquefiable soils more often. We design pile foundations and well foundations in these soils. So currently in Indian codes, we do not have any guidelines on how to account for these liquefaction effects while designing pile and well foundations. So as far as we are concerned, we just assume the soil to disappear and then design the foundation for it. But after this course, I really got insight into what liquefaction is, how it affects the structure, how to account for in design in future when the codes come, what are the effects and how these come. And I would like to thank Professor Gopal sir for giving such a wonderful 5 day session because this is such a specialized topic and the sessions were not only just informative but also it was thought provoking, exciting, and only a person with true passion and interest in the subject could make such topic exciting. And the assignments which were given were also very engaging and it helped us to understand the topics further. And as far as the logistics and other organizing things means organized by NIT Jalandhar, it was all top class. The organizing committee did a great job, gave us information on daily basis, gave us the PPTs, and I would like to thank HOD sir because in the inauguration he has mentioned that you pursued him for this course, and because of you, you are a big reason for this course to happen. So I would like to express my thanks for giving such a great opportunity.
Very good afternoon to all. Myself, Vipendra Singh Jinkwan. I am currently currently pursuing my PhD from this institute. So, on the behalf of NIT Jalandhar, I would like to express my sincere thanks to Gopal sir. So, he came from such a Cambridge University, and so the all the lectures which were which shows the dynamic experience of his on the field of this soil dynamics. So I would also like to thanks Dr. Nehotri and Dr. Senthil sir for organizing this event. So as I'm not from this research field, but the lectures were very informative, and the sessions were very thank you so much, sir.
Good evening, all. I'm Riya Binoy, MTech second year student of NIT Jalandhar. I'm really happy to see uh, all all these many participants attending the class very eagerly, and I'm here to thank Dr. S.P. Gopal sir for the wonderful lectures. We started with failure mechanisms, like very minute things from earthquake, how the soil liquefies, how the liquefaction is modeled in lab. He uh, helped us to visualize the things which happens in the labs of Cambridge University, from where he is. Okay, and it was very interesting, and he took the class in such a way that the topics were very simple to understand. He broke down every concept for us, so that even the BTech third year students were able to grab the concept of earthquake, liquefaction, and all those things. And it was a wonderful opportunity for us to get to know all these kind of things, the research works going on in Cambridge University. And really, we are thankful, sir. And Dr. Agnihotri sir, he explained us the pile foundations, every how do we solve the complex problems. He even explained uh, the simplest geotechnical equations of pile bearing capacity we learned in BTech. He explained each and every denotations, every equations, every letters, I mean, every I mean, whatever the questions. I mean, sir, you explained it very well. Like, I was very happy to see that someone of your post, explaining everything for us. Like, we are of BTech students, even though many research scholars or we MTech students were attending the class. You know, both the expert sections were very simple to understand and grasp the concept, and we are very thankful to you, sir. And Dr. Sendil sir, like the he, Dr. Sendil sir organized the whole program. He helped us coordinate the whole program. He was always there with us. He guided us with every instructions, and his class on abacus was also very informative. We all got to know, like, we were not familiar with abacus. We all got to know how to design a pile foundation on abacus and pile and soil interactions. And sir, the class was very wonderful, sir. Thank you. And I would like to thank Sindhil sir and Agnihotri sir for the for organizing such a wonderful program on dynamically loaded piles from failure mechanism to design. We are grateful for you to use for providing us such a wonderful opportunity for such a wonderful program under GIAN program, and we are thank you, sir.
Can I have 1 minute? Just want to invite you. Hopefully, we still connect this, yeah?
Work. So I thought I'll make some. Why does it not click into action? Will it work? Uh, that's my computer. Should do this. Okay. So just since I had such wonderful hospitality shown to me here, I thought I should end by inviting all of you to Cambridge. So this is a CREST conference. It's on sustainable methods in construction. The series started a couple of years. Uh, we had three so far in Kyushu University. Now it's our turn to run in Cambridge. So it will be a really good opportunity for you guys to come and have a small taste of Cambridge for a short period of time. And we'll be happy to show you our labs and also things that are happening at the Scorpion Center. We've got a few keynote lectures. This is Abir Alchaba, who works on sustainable concrete. One of our former PhD students now in Texas, Alexandra, and our good friend Hemant Hazarika from Kyushu University. There'll be more speakers, of course. At the moment, this is just the initial go at putting some posters together. I showed these in IIC Bangalore as well, and a lot of people said this is a good area and they'd like to come. So I thought I'd extend the same invitation to all of you. So do take the opportunity if you can, and it's a nice time to come to Cambridge. September is always the best time to come to Cambridge. British summers are English summers are really nice because you have sunrise at about 3 or 4 in the morning, and the sun doesn't set until about 10 or 11 in the evening. So the days are very long. We'll pay for it in December when we have about 6 hours of daylight and the rest is all night. But summer is the time you want to come. Okay, so that's the pitch for our conference. I'd like to also say how enjoyable it was for me to come to NIT Jalandhar. I never been to Punjab before. Uh, I went to Roorkee several times, but landed Delhi, take the road trip, and that doesn't come towards Punjab. I think it goes away towards Meerut and to Roorkee. But it was really great. I had an opportunity to see some of the sites. And I'm also thankful for you guys because in the middle period, one day my throat was really not up to it. I had some throat infection, but you patiently listened to my croaky voice. Now I'm much better, and now that it's all coming to an end, it was really good. But the lecturing is one thing, but what any lecturer will enjoy most is the participation. The way you are asking the questions, and there were a few of you who are always stopping me at the end or sometimes even in the middle of the lecture and say, "What about this? What about that?" That is really uh, the mark of success of any lecturer is usually measured by that. That means that you're engaged, your brain is focused, and you have some thoughts about what is being said, and you want to query further. Perfect. That's how it should be. Okay? And I really enjoyed all that. And it also remains for me to thank the organizers, obviously Professor Agnihotri sir for chasing me around and until I came, and I did come. I did say I'll come. I did come, and again he left no stone unturned. Almost I did zero administrative work. GIAN programs are always loaded with a lot of administration, as I'm discovering now, all the forms to be filled and so on. He took care of all of that. and along with Senthil as well. And the hospitality here is unparalleled. You almost become part of the family. You come here, and mostly I was eating either with a professor or with Senthil. Senthil sir, it was great, and it's all has also been lovely meeting all of you. So all the very best in your careers, and keep focused and keep working hard. You will achieve what you want to achieve, no doubt. Okay, all the best.
Last one.
पहले एक्सटर्नल को कर लीजिए फिर इंटरनल को सेट।
अच्छा। Thank you very much, sir, for your invitation. Hope we will plan together. But I think the EGRWAC also same time, sir. EGRWAC. Achha, October. Okay. Right, sir. Also, I would like to thank the reviews which you have given. It's very nice. Now let's call the course coordinator as well as the head of the department and Professor Gopal sir. Sir, please come forward for distributing the certificate. Yeah. Mr. Aman Garg. Yes, sir. One by one. Aman Garg. Oh, sir, 1 minute, sir. Miss Yamini. Yes, please. No, please say something. Okay. No, no, he said no. Dr. Avinash. Yes, Mr. Tarun. Sonu. So we'll keep these steps standing. Standing. The standing.
In the back.
Shall I?
इतना मार्केटिंग कर रहे हो ज्ञान के
Mr. Surender. Mr. Surender. Yes, please. Mr. Ramandeep. Mr. Ankit. Mr. Ankit. Yeah, on behalf of. Yeah, actually, just now met. Mr. Ankit, on behalf of. Mr. Abel. Yeah, yes, please.
You refuse to collect it? Or is this you? Okay.
I think this surname, what is this? Karvabalang? Yeah, yes, please. That's
You know the
yeah.
music about your surname. It's complicated than my surname.
Acha, yesterday.
It's the spelling that is.
Mr. Kunal? Mr. Kunal? Yes, please. Mr. Neeraj? Huh. Mr. Pavan? Yes. Mr. Sonu? Yes. Miss Ria? Yes, please. Mr. Abhishek? Mr. Abhishek? Yes, please. Mr. Rajat? Mr. Rajat? Yes, please. Mr. Shagil? Shagil? Sagil? Sahil Bhatti? Yeah, Sahil. Yes. Yeah. Another one, Sahil Thakur. Sagil Thakur? Mr. Srishant Anand? Mr. Bikran? Mr. Saurav? Yes. Mr. Pravesh? Mr. Vipendra? Mr. Nitish? Mr. Akash Deepak? Akash Deepak? Yes, sir. Last one. Yes, sir. Sir, let's have a group photo. Sure. Yes, please. Please come. Sorry, sir. Follow. Sorry, we keep this.
हेलो नहीं चल रहा advice, then that's grateful that visible. So I am grateful that you have accepted our invitation and come all the way from Cambridge for this GIAN program. We are really very thankful. So with this is the end of this program. We will miss you all. This was very nice program and lectures were very interesting. All of you have given feedback. You have learnt a lot. All of us have learnt a lot from his vast experience. Thank you very much, Gopal sir. Thank you.